Hi, yeah, I'm Peter Bernath, and I'm at several institutions, mainly Old Dominion University in Norfolk, Virginia, but also a research professor at University of Waterloo. And really, I'm a spectroscopist, so like spectra of the atmosphere, record laboratory spectra, have done astronomical spectra, and now, of course, I'm into applications, and you're going to hear about the applications rather than the spectroscopy. And it's all about this atmospheric chemistry experiment, which is a small science satellite. And I'll explain a bit about the satellite and how it works. And then the applications are fire chemistry and plumes from volcanoes. So I'll get into that in the sort of second part of the talk. And the original proposal went out in 1998 to the Canadian Space Agency. And of course, we had a scientific goal to look at ozone in the stratosphere, particularly, and above Canada in particular, in the winter and in the spring, when you have ozone declines. And in order to do this, we had to do a number of things, including measure aerosols, as well as a whole bunch of molecules, which we still do. But now we've been up almost 18 years, and so I would say the main focus is on climate change and looking at trends in atmospheric composition, which I'm not going to talk about at all. But lately we've returned to look at aerosols and ozone, and some of that work I'm going to present now in this talk. So the timeline here, the proposal was written when I was on sabbatical in Brussels in Belgium, and my wife helped me get the proposal together, and we sent it in. And 5 years later, NASA launched us in 2003. So that's relatively short for a satellite mission, as some of you know. And in 2004, we started collecting data. And as a science mission and not an operational mission, the planned lifetime was 2 years. But of course, it's been extended and extended, and this August will be the 19th anniversary on orbit. Um, so it's a small satellite, it's a meter across, and it's always pointing at the sun. So there's a solar panel in front that gives you the power and some batteries on board, and it points at the sun even when the sun is behind the Earth. And so we make measurements only during sunrise and sunsets. And so this is an artist's conception, and this is the limb of the Earth, so-called. And when the sun passes through the limb of the Earth, we record an absorption spectrum. So the sun is the source, the sample is the atmosphere, and we have an infrared spectrometer on board, and I'll talk about that in a little bit. So this is a picture of what it actually looked like on the ground, not an artist's conception. This is at David Florida Labs in Ottawa, or in Nepean, actually, I guess just outside of Ottawa. And there's a person's head back here for scale. And this is us, the family here, standing in front of the shakers. So this does the vibration testing behind here for the instrument. And to get back to how the measurements are made, this is called solar occultation. So the sun is here and it passes through the limb of the Earth. And there's a sunset depicted here. And so every 2 seconds, we take an infrared spectrum. Or to be precise, we take an infrared interferogram, and then that's transformed into a spectrum on the ground. And so as sunset, in this case, would take maybe a minute. So we would get a sequence of about 30 absorption spectra with different tangent heights through the Earth's atmosphere. And on the ground, it's inverted into atmospheric profiles. And so this is a typical profile of ozone. Here is a function of altitude and ozone concentration here on the x-axis in this plot. And the orbit is quite important for these measurements. And because you only get one sunrise and sunset per orbit, you get this very strange plot. So on this plot, on the x-axis is time. This is months for a year, and the satellite observations repeat in latitude. So the y-axis is latitude in degrees. And so blue here is a sunrise, and then red is a sunset. And so it makes these high latitude measurements for a while, and after a month or so, sunrises, or they switch hemispheres, and you get some tropical mid-latitude measurements and so on. And so you get a global picture, but it takes a month or two to get a global picture of this. So you have to be a bit lucky to hit what you're looking for. But we are, and after 18 years, we've got lots of data. So this is the instrument here. It was built in Quebec City by ABB, and unfortunately, they didn't put a ruler in, but this is about 2 feet across down here. And you're looking at the telescope and a sun tracker, and then electronics box. And then this large thing is a passive cooler that cools the detectors, the infrared detectors, by pointing to deep space. So the radiation goes out, nothing comes back, and it cools down to about 80 Kelvin. And on the other side is the interferometer. So this is a so-called Michelson interferometer. There's a beam splitter. The light comes in, it's split, and one arm goes here, and the other arm goes the other direction. It gets recombined and then sent to two detectors, two infrared detectors. And as this arm rocks back and forth, the light interferes with itself and records, and it's digitized, and the so-called interferogram is recorded, sent to ground, Fourier transformed into a spectrum, and that's what we analyze. And just so you get a sense of what the data looks like, this would be a typical occultation sequence. And on the right is the tangent altitude, the minimum altitude above the ground in kilometers, which is also retrieved because we're not totally sure of the pointing. And so up high here in this sunset, the only thing you really see here is CO2. But if you look more closely, you see CO and NO, and the NO is actually from auroral activity. But then as you go deeper and deeper and closer to the surface of the Earth, the other molecules come in. So water starts to come in here, about 1600 wave numbers, and then ozone here. Then at 3000, this is methane that comes in, and so on. There's more water here. And the basic idea is very straightforward. The position of the feature tells you what you're looking at, and the depth of the absorption tells you how much you have. You need, of course, laboratory measurements for all of this, but they exist. And so our big claim to fame is more molecules than anybody else by far. So current version is 4.1, 4.2, and the new version 5 is going to come out this summer, sort of July and August or so. And I'm not going to go through the molecules, but just to say that it's all of these molecules that give you a sense of what's happening in the atmosphere. And it's a very powerful technique to look at the chemistry and also the dynamics of what's happening in the atmosphere, both in the upper troposphere all the way up to the lower thermosphere. So for lower thermosphere, we can actually see CO2 and CO and NO up high, as I mentioned before. And the latest version will have two new molecules, HOCl and HFC32 in it. And this is really a unique data set. As I said, there's nothing like it. And we also have some imagers that is take pictures of the sun. And these were contributed by the Belgians, in fact. Because I was on sabbatical, I asked them, and they said, okay, they could do something. And so this is a sunset here, and this is how the sun's image distorts. But from the extinction of the sunlight, you get the extinction as a function of altitude here. And we have two imagers, one at 1 micron wavelength and the other at 0.5 micron. The 0.5 micron imager never worked very well. But the 1 micron imager looks real good now. So the current version 5 of the imager, so our measurement is in blue, and so extinction in per kilometer is on the x-axis, altitude on the y as usual. And the standard in this is an instrument called SAGE-3, which is on the space station, the International Space Station, a NASA instrument. And you can see we agree quite well now with the SAGE-3. And another example here. So we have a very good product giving atmospheric extinction at 1 micron, which is, of course, very useful for clouds, aerosols, volcanic plumes, and so forth, as you'll see. So now to get down to some science. So we're not looking at ordinary fires. We're looking at pyrocumulonimbus clouds, so-called pyro-CBs. And this is fairly new research. So this is, I better go through the definition here. The real pioneer in this is Mike Fromm from the Naval Research Lab. And this is his definition. The pyro-CB is a fire started or fire augmented. I have to move this thing out of my way here. Uh, um, Thunderstorm that is most in its most extreme manifestation injects huge abundances of smoke and other biomass burning emissions into the stratosphere. And this is a picture taken from an aircraft, so you can see actually what's happening. So this is the fire plume in the troposphere. Then the tropopause is here, and then it's punched into the stratosphere, and you can see how the character of the plume has changed, and it's now very laminar. And in fact, the stratosphere, as you know, has a temperature inversion. And so the airflow in the stratosphere is very laminar, hence the name stratosphere. And so this is the pyro-CB. So that's what we're talking about here, not the ordinary, if you like, fires in the troposphere. And of course, the most spectacular pyro-CBs occurred in late December 2019 and early January 2020, and they were the Australian fires. And the nickname for this, if you like, is the Black Summer. And there's a picture from orbit from this VERS instrument, another NOAA operational instrument. And there's a picture here of Australia and this southeast corner here of Australia is blown up over here. And the VERS has infrared channels, so that's sensitive to heat. And so that tells you where the actual fires are. And there's a false color here, so they're colored red. And so you can see the fires essentially stretched from Melbourne to past Sydney, and the smoke is blowing out over the ocean here. And this was an incredible event. And of course, you all have seen these pictures of the fires on the ground and the devastation that they caused. But they also changed the chemistry in the upper atmosphere, in the stratosphere, and that's what I'm going to talk about. So here's two other satellite instruments looking at this pyro-CB. And this one on the left is Calypso. So this is a French-American LiDAR. And it's on orbit, and it fires a laser towards the ground. And the return signal is recorded with a 1-meter telescope on board. And you can see here, these are regular clouds. Since they're up at 10 kilometers, they're probably high cirrus clouds made up of ice mainly. And you can see the laser doesn't even penetrate here into the ground. But over here, this is clearly in the stratosphere. This is 20 kilometers now. And this is the pyro-CB cloud in the stratosphere. And over on the right is another satellite or data derived from a satellite. This is OMPS, the OMPS instrument, again on a NOAA operational satellite. And they make an aerosol index. And this aerosol index you see is greatly enhanced here, just near New Zealand. And this green star is where the ACE measurement hit it. And so we have data for that point. And here's some of it. Some of it was published earlier in 2020. And on the left, as in Mike Fromm's definition, these are the organic molecules, the pollutants, if you like, that have been injected into the stratosphere. So the tropopause, maybe 12 kilometers here, and a dozen or so of these organic-y things have been observed by the ACE satellite in the stratosphere, very much enhanced. Things like HCN, which is a famous fire molecule, by the way. At least 90% of it is produced by fires, and so on. And then on the right is some unique things that we're able to do with the ACE instrument that no other satellite instrument has ever done before. So what we did is we removed all of these gas phase lines, all 46 molecules, we removed them. And what was left over we call residual spectra. But they're in fact the spectra of the clouds and the aerosols. And in this case, we're looking at smoke spectra. And the Australian fire smoke spectrum is here in red. And it's not featureless at all. So some of you might think, well, it's soot, black, there's not a whole lot to see, not, and even in the infrared. And that's not the case. It has clear features like this is a carbonyl stretch here and various other features, which I'll come back and talk more about. So this tells you something about the surface of the smoke that's going to cause the chemistry that, among other things, depletes the ozone. Uh, okay, so we wrote this up. These are observations and called it "Wildfire Smoke Destroys Stratospheric Ozone," and this appeared in the journal Science, 18th of March, 2022. And what we saw was without precedent. So remember, this is mid-latitude, and what we saw was increases due to the soot from formaldehyde, chlorine nitrate, chlorine monoxide, HOCl, and decreases in ozone, nitrogen dioxide, and hydrochloric acid. And so these perturbations were affected the ozone in very unexpected ways, and the changes caused by smoke were without precedent. And of course, there was a lot of interest in this around the world. Hundreds of stories appeared around the world in various media. So the same day that the paper appeared, the 18th of March, 2002, the Wall Street Journal wrote a long article on it entitled "Extreme Wildfire Smoke Poses New Threat to Ozone Layer, Research Finds." And um, as you might imagine, there were stories in Australia. There's a very nice and very well-written story in ABC, the Australian Broadcasting Corporation, wrote this story about this work. And in Europe, it was picked up by this VRT. V is for Vlaams. So this is a Flemish part of Belgium. And this Vincent Merck wrote a nice article. Google Translate is helpful here, on the whole thing, and had this diagram on it. And you can see the labels in Dutch here. Flemish is Dutch. Troposphere, ozone layer, stratosphere, and fires here down here. So caused a lot of interest around the world. So to get back to some of the science, so this is the spectrum of smoke again, with the gas phase molecules removed. And it has this carbonyl stretch, a CH stretch, OH stretch, and that's a carboxylic acid feature. So that's consistent with carboxylic, an organic acid on the surface. But more interestingly is also features assignable to water. So this is a water libration. So water doesn't rotate in the solid or liquid. It librates. It vibrates back and forth. And so this is a librational feature of water. And then this shoulder over on the right is the OH stretching feature. So the surface of this smoke is both acidic and hydrated. So that gives a clue onto the kind of chemistry that can take place. So again, coming back to the 1 micron imager, so we looked at monthly averages of the extinction due to smoke. And again, the x-axis here is the 1 micron extinction, or the extinction at 1 micron, as a function of altitude, and the black is the average for the entire 2019 year. So this is mid-latitudes in the southern hemisphere. So not tropics or polar, just mid-latitudes. And you can see in January here in red, you can see the layers, the smoke layers still. But then in the other months, this is the first half of the year, the aerosol has spread out, and the extinction in the southern hemisphere has increased for the first half. And then for the second half of the year as well, even in November, this red trace here is higher than the 2019 average. So essentially, there was smoke in the southern hemisphere mid-latitudes for all of 2020 from the Australian fires. And it affected the chemistry. And so this is ozone. Altitude again on the y-axis, and what's on the x-axis now is what's called an anomaly. So that's a difference from the average. And for the first couple of months, the ozone actually increased. And that's quite understandable because of all of these organic molecules. So these organic species, when they're in the troposphere, they get oxidized to carbon dioxide and water, and the byproduct of that oxidation is ozone. So the ozone pollution that you all unfortunately breathe originates from organic molecules. And of course, these organic molecules were injected into the stratosphere. And so for the first couple of months, they caused enhanced ozone because of this kind of tropospheric chemistry pushed into the stratosphere. Um, but then the organic molecules in the stratosphere have lifetimes that are fairly short, a month or two, and so then they're pretty much gone. And then the ozone declines set in, and starting May and June, and so the decline here is 10 to 15%. So this isn't an ozone hole or anything, but it's a pretty substantial reduction in the ozone. And I remind you, stratospheric ozone protects us from the UV radiation. Um, and so then it continues really for the whole year, these ozone declines, and even partly into the following year. And other molecules, and here's the chlorine-containing molecules, which tell you something about the chemistry. So HCl, so this is all the years of HCl here up to 2019 plotted as a function of altitude again. And then this is really May, June, a couple of weeks in May, a couple of weeks in June, averaged. And the HCl in red here has dropped by a factor of 2 or more. And curiously, chlorine nitrate has increased by a factor of 2 or 3. And HOCl again has increased dramatically. Chlorine monoxide has increased somewhat. And the implications for this, so this is hypothetical. So there's no real lab work about the chemistry that takes place on these kind of smoke particles. So here's some possibilities. So HOCl could react with HCl on the smoke surface and make chlorine. The chlorine gets photolyzed to make chlorine atoms, and the HCl decreases. And the chlorine atoms then run in something called the clock cycle, which destroy ozone. So chlorine reacts with ozone to make ClO. The ClO reacts with oxygen atoms to regenerate chlorine atoms, and it cycles around destroying ozone. And HOCl also photolyzes to make OH and chlorine atoms, and so chlorine monoxide would increase because the chlorine atoms are increasing. And another kind of chemistry, the N2O5, is hydrolyzed during nighttime on these hydrated surfaces to make nitric acid. And so then that causes the NO2 to decrease. So this is all somewhat speculative at this stage, but is at least plausible chemistry caused by the smoke. And what are the implications? Well, these extreme wildfires are becoming more frequent because of climate change. And the 2021 IPCC report talks about this and gives the evidence for this. And these pyro-CBs, as you see, perturb the chemistry. The hydroxyl chemistry, which I haven't talked about, the reactive nitrogen, like NO2, is perturbed, and particularly the halogen chemistry. And the ultimate effect is to destroy ozone. And so, as you're all aware, I'm sure the Montreal Protocol has banned the production of CFCs. But these CFCs have a very long lifetime. And so it's thought that by 2015, the anthropogenic contribution of chlorine to the stratosphere will have pretty much gone away, and we'll be back to the sort of 1980 ozone layer, and the ozone layer will have said to have recovered. But these wildfires then, these very large wildfires then have the potential to delay the recovery of the stratospheric ozone. So what about other clouds and aerosols? Well, we've been spending quite a bit of time now looking at them with these residual spectra. And we've seen 8 or 9 of these types of aerosol and cloud spectra. We see polar mesospheric clouds. So this is ice up at 80 kilometers. We see polar stratospheric clouds, and have written a paper on this under review for Science. We see cirrus clouds, ice clouds, upper stratosphere. We see volcanic ash very rarely. It turns out the volcanic ash seems to settle out before we hit it with the instrument. But we see lots of sulfate aerosols, typically from volcanic eruptions, and even background aerosols as well. And I'll talk a bit about that. So to remind you of the importance of sulfate aerosols, so they're also in the troposphere, but what we're talking about is stratospheric, the so-called Junge layer in the lower stratosphere of what are sulfuric acid droplets. And the source of this is injection from large volcanoes. Most volcanoes don't inject anything to stratosphere, but large volcanoes do inject SO2, which ends up making sulfuric acid droplets. And in the background case, when there's no big eruptions, the main contribution is OCS, so carbonyl sulfide, which has a long lifetime in the troposphere, gets oxidized in the stratosphere and maintains this layer. And of course, this layer has big climate impact. It scatters light back to space, so the surface is cooled because some of the sunlight is reflected back away from the surface. And there's actually a small amount of heating due to infrared absorption of these particles in the stratosphere. So it's a big deal in the climate system. And of course, we've studied a number of these. And in the last few years, the Reikoke volcano is one of the very largest ones. And this is a picture here, I think from an aircraft again. And it has this characteristic flat top that you'll see again in another picture when I get to the Tonga volcano. And so to remind you, this Reikoke volcano um, was dormant for 95 years and erupted in June of 2019. And this is a picture. It's an island in the Kuril Islands, just off the eastern part of Russia. And there's nothing on it. I don't know if there's 1,000 meters or something other than the volcano. Um, uh, and it blew up in a very spectacular fashion. And again, coming back to the 1 micron imager, so the background extinction is in this orange color. And then when we hit the Reikoke plume, one of our occultations is blue here from the imager. And when you take the spectrum of this feature here at about 15 kilometers, you see that it's a sulfate aerosol, which is essentially pure sulfuric acid. So just in case you have any doubts on this score, there's these characteristic features here, and I have a lab spectrum recorded of sulfuric acid, and there's 1, 2, 3, 4, 5 characteristic infrared features. And if you come back here, here they are, 1, 2, 3, 4, 5. So there is no doubt that these plumes are essentially pure 100% sulfuric acid. And of course, we can do more than say that. We can determine composition. So the model here is in orange. This isn't a great example, by the way. There are much better examples, and I'll show a few coming up. And so the kind of information we get, this is 65% sulfuric acid, and the error is less than 1% on this. And so we have very precise determination of the composition of the sulfuric acid. And the size, so the median radius is 0.28 microns for this, obtained from fitting the observed spectrum with a model. And of course, you can actually see things change. So you can, here's an interesting study from the Reikoke volcano. So this is in the Arctic. So a lot of the plume from Reikoke went into the Arctic. And we have got quite a few measurements in the Arctic then. And in fact, there's a paper that's utterly wrong that says this plume is is smoke. It's not smoke, it's sulfuric acid. So here, because we're in the Arctic, the tropopause is 9 or 10 kilometers. And this is the change in the composition as a function of altitude in one plume. So we have different ACE measurements at different altitudes. And you can see the composition is going from about 63% up to about 73%. And I'll remind you that the temperature is going up. So it would appear that the particles are evaporating. That is, the water out of the sulfuric acid is evaporating, and the sulfuric acid solution is getting more concentrated. And consistent with that, over here for these various points is the diameter, the radius rather. And you can see the radius is clearly getting smaller as you go up in altitude. And I should comment that no kinds of measurements like this have ever been made before, essentially because nobody's had these kind of spectra before. And I'll say a few words now about the most spectacular recent volcano, this Hunga Tonga Ha'apai volcano that blew up 15th of January. So it was an underwater volcano, uh, and it went off with a tremendous explosion, considerably larger than a nuclear bomb. And it had atmospheric pressure waves and gravity waves and a tsunami and so forth. And this is a picture from orbit, and you can see the ash in this characteristic flat top plume again, I think from a Japanese satellite. Um, of course, we weren't measuring there, unfortunately, when the thing blew up. But a few days later, about 2 weeks later, in February, we were measuring. And so these were the measurements, I think, on February 4th or so. And the occultations in red here are the ones that hit, and a couple of these occultations here hit the Tonga volcano. And this is the operational product. So you can see two of them have the enhanced SO2. And then from the 1 micron extinction, you can see several of them are also enhanced. And this peak here is up at 28 kilometers. So apparently, although it isn't shown here, other satellite instruments have seen perturbations up to 50 kilometers into the lower mesosphere. But we can do a little more with this. So this is the 1 micron extinction now from a measurement in the 6th of February. And up around 25 kilometers, there's a peak. And the SO2, we pushed the retrieval, that is Chris Boone, the retrieval scientist for ACE, pushed the retrieval up higher. And you can see at 25 kilometers a SO2 plume. And if you take the spectrum, the residual spectrum at the peak, this is it, the characteristic sulfuric acid spectrum. And in this case, again, about 62% is the composition. By the way, the compositions we're seeing don't match the canonical, whatever it is, 74% or whatever that is assumed for the models and for the climate models. It is not true. We see things from low 60s, occasionally even 50%, up to 75, 78%. And so the canonical number for the composition of sulfate aerosols is not correct, mainly because nobody had any measurements until we came along. And we have a paper coming, well, it's under review on this very topic. So for this size, 0.27 microns, 62% sulfuric acid here. And you can see the model reproduces the observations very well. And I better start wrapping up. So this ACE FTS is an incredible instrument. Not only does it see climate change, but from changing atmospheric composition, it now can characterize particles, all kinds of clouds and aerosol particles, in a way that was not possible before, mainly because nobody had these absorption spectra. And we can find new things, new chemistry that's catalyzed by stratospheric soot that alters the stratospheric chemistry and destroys ozone, stratospheric ozone. So some acknowledgments. My wife Robin, as always, without her, this mission wouldn't exist. My group in Waterloo, Chris Boone, Jeff Krause, Johnny Steffen, Dennis Koch, and Mike LaCour. And my group at Old Dominion University, Ryan Johnson, Keith LaBelle, Randika Dodangodagi, Doug Cameron, and Jason Sorensen, all of who worked on ACE data at one time or another. And I'd like to end with the comment that the success of this mission is because it's a spectroscopy mission. It's a spectroscopy that has the power to tell you about the 46 molecules that we can detect, about the aerosols and clouds and their composition and size. And so we're really a spectroscopy mission that is doing atmospheric science. And with that, I'll stop and take any questions or comments.
Thank you, Peter. That's really a tour de force, including how fast you were able to get your mission up. I had a postdoc at ASU working with a planetary geologist, and he was on the Galileo team, and it was 20 years from their first meetings until they started getting data. So You're to be commended for that. I had a couple of questions, and then others, please jump in. And these are just because of my ignorance about how the atmosphere works. Um, I recall when Pinatubo erupted, and I was in Arizona, and we had a noticeable cooling of the temperatures in the summer for 2 summers, and I recall the discussions being that the ash plume was concentrated in the northern hemisphere, and that there wasn't any effect to the south. So my question is about how much mixing is there, say for these pyrocumulonimbus clouds from Australia. How much of a latitudinal coverage would there likely be? I mean, does it tend to stay as a concentrated blob, or does it diffuse out? And how do your measurements help pin that down?
So it depends whether you're in the troposphere or the stratosphere. So to go across the equator in the troposphere takes a year or so. And so normally the circulation in the troposphere is, at one latitude. So, things take a week or so to go around the globe. And so that's kind of typical. But once you're in the stratosphere, things are different. And for the Tonga volcano, that we can actually see that within a couple of weeks, maybe a month or two, it went across the equator. We see the plume crossing the equator in the stratosphere because the circulation is very different in the stratosphere. The main circulation in the stratosphere, there's Brewer-Dobson circulation, which sort of upwells in the tropics and then goes to the winter pole, I think, mainly. And so it's really very different. And I'm no expert. I'm not an atmospheric dynamics person at all. So,
Great.
but that's the general idea.
Yeah, and a related question. So you're describing all of these chemical characteristics that you can infer from your measurements. Are there balloons that go up that actually sample in different parts of the stratosphere or troposphere, and to confirm what you're getting spectroscopically?
Yeah, there are balloons, notably in the States. The JPL has a balloon program. They launch from New Mexico, typically in September. And I don't, I think the COVID kind of knocked them out, and I'm not sure. I think they're going to start making measurements, but they're very localized. And so helium balloons go up to about 30 kilometers or so, but they're in one spot. And you kind of have to do this measurement at turnaround, which means that when the stratospheric winds switch direction, because if you don't, your instrument then is, unrecoverable. It's out over the Pacific or Atlantic Ocean and you're doomed. Um, so you have to launch at a certain time, at a certain location, and they're not that cheap either, by the way.
Right. Okay. Um, other people who have some questions? I know there's some interest that's been expressed in getting the recording, which hopefully will work. But anybody else, just feel free to ask.
This is John Bailey at Oregon State. Is this data set up and the equipment good for, doing kind of long-term trend analysis for methane or something like that? Or is that
Oh
just
yeah, we've published a paper that's referenced in this talk. In fact, I've published a couple of papers about long-term trends and methane and N2O, and ozone and CFCs and all of these uh, molecules, all 46 of them, well, 44 in the paper actually, are we have the trends, we have the global trends. Now, mind you, we're remote sensing, and our trends for many molecules are unique in that, like chlorine nitrate, nobody else is doing it. But for other molecules, the ground-based people are much more precise and have much better records than we, like for methane. So we can't, for some molecules, we're the only game in town and we're the best by definition. But for other molecules like methane and N2O, we get altitude profiles and we can see what's happening as a function of altitude. But we're nowhere near the precision or accuracy. We're talking about 4 or 5%. And the ground-based people are way better than that.
Peter, this is a question either for you or for anybody in the audience about these mega fires that have these pyrocumulonimbus clouds. How many of these have been documented in the last, say, in the last 20 years? I mean, Australia was clearly a huge fire. The ones that we had in Oregon 2 years ago, were those large enough to give this kind of a signal, or are there others recently that you're aware of, or others are aware of, just to get a sense of how rapidly is this phenomenon becoming more problematic?
Well, I think to answer some of that, yeah, I think the New Mexico ones were pyro CBs,
Hmm.
and I think the Oregon also, and the Northwest fires. One of these diagrams I showed had these Pacific Northwest fires of a few years ago were there. And this year, there's actually a news group that you can sign up to that reports these. And there's some Siberia, and just a few days ago, I noticed there some pyro CBs in Siberia just started out, and so on. So they're quite frequent now. Not as dramatic as Australia, but every year there's lots of them.
I see. Thanks. And my last question, at least for now, is the suggestions that we may require some geoengineering methods to cope with global warming, and the suggestion of trying to replicate the atmospheric effects of eruptions like um, Pinatubo. I mean, could your instrument help determine how effective such approaches would be if people started putting these artificial clouds up? Would you be able to measure those and say whether or not those are likely to be reflective in the way that the volcanic clouds are?
I think so, but the experiments are not so easy for us to get. But certainly we have natural experiments, so we can look at the composition of the effect, around a volcanic plume and say what the effect on the different chemical is. So, yeah, in that sense, this is the problem is always unintended consequences, right? Like as soon as it comes up, everyone says, rabbits in Australia or something like
Right,
this.
right.
Yeah. So certainly our data can answer what a fleet of aircraft putting SO2 into the stratosphere might do. Although the modelers think they can do it better than we can measure, but certainly our
Yeah.
data would give real validation of what the models are saying.
Yes. So we have several members of the audience who are involved with civil defense and on the ground consequences of fires. And I wonder, Jeff Rubin, or any of the others, if you have any thoughts on this kind of new measurement and how that might be useful for the work that you all do. We have some BC wildfire folks here. It's like the high school teacher trying to get
Yeah.
students to respond.
I will comment about the big BC fires that were a few years ago. So
Yes.
I had several questions from reporters. So is this big ozone decline? Did it happen with the BC fires?
Yeah.
And and the answer is we're not totally sure because, of course, they happened in the middle of August and we weren't measuring in BC then. So then we had a little bit of data later, and we looked at it and we couldn't see any big changes, for example, in HCl. So it's sort of up in the air on that one. It might not have been big enough, and we certainly didn't hit it at the right time. So with these kind of occultation measurements, on the plus side is we get a fantastic amount of data that nobody else can get. Uh, uh, on the downside is you got to be there and hit it right on, and that doesn't always happen. Now, if you're in the Arctic and the Antarctic, probability is actually pretty good, as you
Uh-huh.
saw from the distribution. But if you're in the tropics, man, you'll wait a couple of months and a much chance here. So we hit Tonga quite well, though.
Right. Right. So, how were you able to get this mission approved so quickly? I mean, that's unheard of timing from a NASA perspective.
Well, yeah. So this is this faster, cheaper, idea that was popular, 20 years ago, and is still popular. So that you can do missions faster and, that are simpler, like one
Mhm.
instrument or one main instrument and cheaper. And they use military grade parts rather than space qualified parts and so on. And so there was a deliberate effort to make this cheaper. Now, cheaper is all relative. So at the time, the cost of this at launch was 42 million, is apparently the canonical. I'm not counting launch. And
Yeah.
NASA provided the launch for free and that was worth about 25 million. But free is all relative. So Canada, of course, kicked in the Canada arm for $1 billion, and the US handed back, a couple of launches for 25 million. So, there you are.
Right.
Yeah, it's a
And
fantastic instrument. I mean, ABB, is really without equal. And real for the Canadians this is a real Canada success.
so from the work that you've done on volcanic plumes, is there a gap that could be filled by another instrument that you could imagine or get involved with a new mission that would be complementary to what you're able to do with ACE?
Well, the big thing now is smaller and constellations. So, the next kind of missions would be, sort of large CubeSats, if you like, and you kick up half a dozen of them, and that gets you much better global coverage. And people are starting to do that, in fact, of course, and commercial um, folks are getting into the business, not just governments and space agencies. So that's kind of one future direction. But certainly you can make the instrument smaller, somewhat smaller at least, and you can make more of them, and it's cheaper. The first one costs a lot, but it's all in non-recurring engineering costs. So the second one is a heck of a lot cheaper.
Right. And you mentioned that you were planning for a nominal 2-year mission, and now you're at 19. How long can this keep going?
Yeah, that's kind of interesting. Everyone asks that, and so 7 or 8 years ago, we did a study. We don't have any propulsion on board, so we're sinking
Hmm.
about a kilometer per year. And so at the time, we thought that we could last up until 2034 when we would start to burn up or would burn up. And we're redoing that. So somebody asked that question again recently. So we're now going to update our estimate here on it because of course there's still atmosphere up. We're at 650 kilometers, and so the friction causes the orbit to sink, and the solar activity also changes things. Um, so maybe 2034.
Impressive. Any last questions from anybody else?
Yes,
Uh, Go ahead.
John Sticks at McGill University.
Great. Hi, John.
Yeah, hi. So I thought that was a really great presentation, and I had some questions about the vertical extent of the ozone in your profiles. It was very interesting that there were ozone depletions, but there were also ozone increases at different altitudes. Do you want to say a few words about that vertical heterogeneity?
Yeah, that's really, I mean, we see what we see. I mean, that's, it, the details have to come out from models, which people are just starting to do. But I mean, we do the observations, and that's what we see. I mean, I can go back to that ozone plot if you want, but I can't say anything other than those are the observations, right? That's the data, right? So the effect is mainly in the lower stratosphere, up to about 20 kilometers or so, and the depletions are around that. So really, the effect is the lower stratosphere, um, not much higher than 20, 25 kilometers here for the fires. But then the fires don't get that much higher. These fires don't get much higher than about 25, 26 kilometers, and so then the effects are all below that.
Right. And that's really interesting. And what do you think about HCl? HCl is a very soluble species, and certainly in the volcano world, there's debate about how high it can get put into the stratosphere because of its solubility. How important is HCl, do you think, in terms of these wildfires and its ability to get up, above 10 kilometers and so forth?
Well, the HCl, of course, is coming from the CFC decomposition in our measurements on the fires. But from
Okay.
the volcano, there is, as you say, some injection of HCl into the stratosphere. And of course, we looked, I had a postdoc here, had a quick look to see whether we could see HCl increases due to the Tonga volcano, and we actually didn't see any. But I think the folks in JPL have also had a look, and they published some papers on Tonga, and they make a comment without showing any data that the HCl may have increased slightly.
Okay, so
But
forgive my ignorance, but is HCl associated then with wildfires?
no,
Okay,
the
okay,
HCl is coming from entirely from the CFCs. There
okay.
may be
So
a
what?
small amount from the fires, but nothing makes any difference. So the
Okay,
HCl is all coming from the decomposition of chlorofluorocarbons by UV light.
right, right. And so what is producing in terms of wildfires? What's producing the free chlorine then?
Well, that is the whole question. That's the
Okay,
chemistry on the. So no one really knows, and so I had some thoughts and some speculations about the HCl reacting on the surface of the soot. But nobody has actually done the right experiment yet, although I'm sure they will now, where you take some kind of soot in the lab and put some HCl in it and put some chlorine nitrate in it and see exactly what you get. And those experiments were done on polar stratospheric clouds, of course, but not on soot. And so this is a research project for the chemists involved in this kind of work to do the kinetics. And so it doesn't exist. So I can't answer your question.
okay, okay. Thank you. That's great. That's great. Really interesting.
Julie Griswold, you had a question.
I did. I wanted to just say thank you very much. That was a great talk. Really learned a lot. I wasn't familiar with the satellite sensor at all. And John, you actually asked one of my questions, really about the sort of the longevity and maybe future plans for this and other maybe similar CubeSat. So that's all great. Thank you. And I'm wearing a volcano hat here, and I am pretty ignorant of atmosphere and all things geochemistry, but I do monitor volcanoes from satellites regularly. And this is really intriguing, and I'm curious to know really what the future plans are. Whether you see this being operational, I gather you have to be pretty lucky to catch a large volcanic plume. But if there were a network of these, or if will there be replacements after it burns up in 2034? What other scientists are using this? Will this become a regular research tool?
I
I guess
can't
that's
really
like,
say. It's been proposed to do follow-ons, and I've proposed some to NASA and so on. But there's certainly nothing planned. So, of course, for volcano research, what people like are nadir sounders as they look down and they get global coverage and they can send out alerts to aircraft and all this. So certainly the operational stuff people want is nadir sounders, not these limb sounders. But if you want to do science, right, and characterize the plumes, this is without peer. Um,
yeah,
but for
outstanding.
operational things, they want to look down.
Gotcha.
Julie,
Thank you
say
very
where you
much.
are. Julie, where are you calling from or located?
Well, I'm teleworking from home, Portland, Oregon, but our office is the Cascades Volcano Observatory, and I work for the Volcano Disaster Assistance Program.
Excellent. Yeah, we've had a few volcanologists participate in our wildfire series over the last couple of years, but I think there's increasing overlap. And Peter, when I first invited Peter to talk about wildfires, he mentioned the volcanic applications of their work, and so that was why we sent the note to Volcano Listserv. But Peter, I don't want to speak for you, but I think part of your goal here was to make some additional volcanological connections that you could talk with in the future.
Yeah, that's certainly one of them to make the the various communities, particularly the volcano community, um, aware of our observations. And as I say, the key paper is now back with the Journal of Geophysical Research on this volcano observations, or the first big paper is on volcano observations. And so something will appear, and I'll try to send it out to people. And it really lays out what we can do and some of the observations that we've made, and the composition. The composition, incredibly enough, is a big mystery. For the plumes, the volcanic plumes. So nobody actually, until we made our measurements, had accurate measurements, and so people just guess. They put a number in. I think like 75% is a number that sticks in my mind, and they stick that in the climate models. And of course, the composition and size is key to all of this, because if you're going to do climate effects of sulfate aerosols from volcanoes and something, it depends on the size and composition of the particles, not just the number that you have. And so I think we can offer some insight into what are reasonable values and how things change with altitude and with time. And that's our goal, not to be operational, but to give some really kind of scientific insight.
Excellent. Well, I think we're at the end of the hour. Peter, if you can stay on for a minute afterwards. And for everybody else, those of you from the volcano world, thank you for joining us. For the wildfire folks, we're not going to have any talks in July, but we've got one from the Nature Conservancy in August, and we'll send out a note a week or so before that. And again, thank you all for participating, and have a great summer.